Hi everyone, we've already learned how to integrate a few different types of function, and so I think now we're ready to calculate some areas, and this video is mainly going to look at how we can actually find areas using polynomials. So as I say, so far what we've done is we've calculated the area equation, or which we call the integral, but we haven't actually calculated areas. So the question is, how do you calculate an actual area under a graph? And that's called definite integration. Definite integration is where you actually put in some numbers and you really work out the value. It's a little bit like working out a gradient. You can find the gradient equation, the derivative, but actually you've got to put numbers into it to actually get the gradient. This time we're working out areas, so we've got to put numbers into the area equation, and I'll show you how to do it. It's got some special notation. So what is definite integration? Well, it's obviously using the integral to find particular areas. Now, if you're going to find a particular area, we need to know the limits. That means the area where we're trying to find. So, for example, if you look at the diagram here, on this diagram, the limits are 6 and 1. We're finding the area between the values of x equals 1 and the x equals 6. They're called the limits. Once we know the limits, we can substitute each of those numbers separately into the integral, into the area equation, and we'll get two different answers. Now, when we put the higher limit in, let's say the 6, for example, in this one, we will get the area from 6 all the way to 0. Then we put the lower number in, the 1, and we get the area from 1 to 0. And then we need to subtract those answers to get the area between 6 and 1. Now, the good news about definite integration is that we can forget about the plus c that we used to have to put on the end of every integral. It doesn't actually matter anymore, because when you subtract two numbers from each other which have a c in them, the c's disappear, they cancel. So we don't need to worry about the plus c. So let's go through an example of how we do definite integration. So let's suppose we want to find the area under the curve y equals 12x minus 3x squared between 0 and 4. Now, I'm going to show you what that looks like. That is the graph. You don't need it to work out the area, but it's useful to know what actually we're calculating. Now, in this particular one, the limits are between 0 and 4. So those are the numbers we're going to put into this into the integral. So there's lots of funny notation with integration, and you've got to be a bit careful with it. So we've got that funny curly s y dx, so the integral of y dx. And since we know what y is 12x minus 3x squared, we can put that equation into that funny symbol instead of the y. So what we actually get is this, and you can see the curly s, you can see instead of y, we've now got 12x minus 3x squared. We've still got that dx on the end. And we've now put these numbers 0 and 4. So the problem is really the 12x minus 3x squared. That's what we're trying to integrate. There are limits between 0 and 4, and you put them on the end of that curly s, the top and the bottom. So the higher number you put on the top of the curly s, and the lower number you put at the bottom of the curly s. And then we still have the dx, as I said. Don't worry about the dx, it just needs to be written there. It shows that we're integrating it with respect to x. Now, that's the problem. We've now written the problem. We haven't actually done anything really apart from just write the problem again in the proper notation. The next thing you do is you're going to integrate that. So 12x becomes 12x squared over 2, which is just 6x squared. And then the 3x squared minus 3x squared becomes minus 3x cubed over 3, which is just minus x cubed. So what we do next is we write that answer down, and we now put it in square brackets. Those square brackets show that we have now integrated it. Now we write the limits on the other end, so the far end, the right hand end, we now put the limits on the top and the bottom of that last square bracket. So there's our integral, and there are our limits. So that's the notation used to solve these problems. First of all, you can write out the problem like the top half with a long curly s, and then when you've integrated it, you put it into square brackets and you move the limits to the other end. So the square brackets, they're there to show you that the problem has already been integrated. They shouldn't be curved brackets, they should be square brackets. So that's what we've done so far. We still haven't quite finished it. We've integrated it, but we haven't put the numbers in. So the next thing, we put the higher number in. So we substitute x equals 4 into that equation. So we get 6, 4 squared. Remember, the 4 squared will come before we multiply by 6 using BIDMAS. So it'll be 6 times 4 squared. And then we're going to subtract 4 cubed. Well, if you do that, you get 96 minus 64, which ends up being 32. Then we put the lower limit, the 0, into the equation. Now, actually, you don't really need to put 0 into an equation. If you put 0 into it, you're always going to get 0. The area between 0 and 0 is always going to be 0. So it does come out as 0. And then we subtract our two answers. Now, it's very easy in this case. 32 take away 0 is still 32. And so that actually, 32 is our answer. The area under the graph between 0 and 4 is 32 units squared. Now we don't know what the units are, so we just call it units squared because it's an area. If you compare that to the graph again, so we worked out the area came out as 32. If you look at that graph, if you look at it as a rectangle, which it isn't, obviously it's a curve, but if it was a rectangle, it would be 12 times 4, so that area would be 48. And we found out that the area under the curve came out as 32. And that 32 might sound very exact for a strange curve like that, but that is actually the exact answer. Let's do one more example. Actually, we'll do a couple more examples. So this example here is a little quick one here. And we've got y equals 3x squared minus 4x plus 10. And we've got to find the area in the range between 2 and 4. So first of all, we'll write the problem out. So we use the curly s between 4 and 2. We write what y is, which is 3x squared minus 4x plus 10. And we put dx on the end. So that's the problem. Now we then have to integrate it. So I've integrated it there. 3x squared becomes just x cubed. Minus 4x becomes minus 2x squared. And the 10 becomes 10x. Remember, I don't need to worry about the plus c anymore. And I put the limits at the other end. So the limit's now 4 and 2 at the other end, on the right-hand side now. Now I put the 4 value in. So I put the 4 value in, and I get 4 cubed minus 2 times 4 squared plus 10 times 4. And I get the answer 72. I then substitute the other value in, the 2 in, and I get 2 cubed minus 2 times 2 squared plus 10 times 2, and that gives me the answer 20. And then I subtract those two values, and I get the answer 52 units squared. So the area of under the graph y equals 3x squared minus 4x plus 10 in the range of 2 to 4, it's 52 units squared. Again, a nice round number. Here's a slightly harder example. This is a velocity time graph example. So the question says, calculate the distance travelled between 50 and 100 seconds by a Formula 1 car that moves with the equation v equals, and it's got quite a long, complicated equation. It isn't actually a very difficult equation. It's just that the numbers are a bit small. So you've got 1 times 10 to the minus 6. That's basically 0.501, which is a very small number. And they are, the second one is also got a small number next to it. But they are really just t to the power of 4, t cubed, t squared, t, and a number. So first of all, we write out what the question should be. Now, remember, we're trying to find the area between 50 and 100. Now, it is the area we're calculating, because on a distance, on a velocity time graph, which is what this equation represents, the distance is the area under the graph. So we are calculating the area. So we write out the problem, and there's our limits, 150, and then there's the whole equation, and it's got dt on the end. Next, we have to integrate it. It's not that difficult to integrate. We do increase the power of t and divide by the new power. It does get quite long, and that's what it comes to. So it's quite a long old thing. But in the end, we've got 0.2 times 10 to the minus 6 t to the power of 5, minus 1.5 times 10 to the minus 5 t to the power of 4, minus 0.0033 t to the power of 3, plus 0.035 t squared plus 60t. and the limits are 100 and 50. So we put in 100 and we end up getting answer 3,550. That's basically how far the car has moved in the first 100 seconds. And then we put the value of t equals 50 and we get an answer of 2,644. That's how far it's travelled in the first 50 seconds. So if we want to find the distance it's travelled between 50 and 100, we have to subtract these two values, and we subtract them and we get 906 meters. And it's really exactly the same as the previous example, it's just it's got a scenario instead. So just looking at it graphically, just so that you can see what the graph looks like, if we actually plotted that graph, we would get that shape there. So what we're doing, we're trying to find the area under that graph between 50 and 100. So when we, that's the red area, that's what we're trying to find. What we actually did was work out the area between 0 and 100 by putting the 100 value in. Then we found the area between 0 and 50. And we subtracted those, and that gave us the red area. That is really what we did. Hopefully that makes sense to you in what you're doing when you're putting values into the integral. So here's the key points. Integration is the exact reverse of differentiation. Hopefully you've got that now. So it helps us to find the area equation, which we call the integral. To find an actual area, we need to know the limits. We substitute each of these limits into the integral to get two different answers, and then we subtract the two answers. Now there's a couple of little things you just need to be aware of. It shouldn't happen to you, but it's just something you should be aware of. When you're calculating the area, it actually calculates the area above the x-axis. So what that means is, if the graph is above the x-axis, we get a positive value, and if the graph is below the x-axis, we get a negative value. So you might find some questions you're going to get a negative answer. The problem comes is when the graph is a mixture of going above and below the axis. If we work out the area in this example between A and B, we're going to get some of it's positive and some of it's negative. So the overall answer is going to be a mixture of the two. And that may not be what you want. It depends on what you're trying to find. So depending on what we're trying to find, it often is best to split up the area into separate sections where it changes from being above the axis to below the axis, and you might need to find those points. I'm not going to give you any questions like that, but that's just something you should be aware of, what happens when you're integrating. So here's the key points again. The only thing I've done with this slide is just at the very bottom, I've just shown you the notation. So you've got the question with the curly s, dx. Then you've got when you've integrated it, you put it inside the square brackets and you put the limits on the right hand side. Then you put the first value, the higher value, into that and see what it comes out as. And then you put the lower value in and you see what that comes out as, and then you subtract those two answers. And that kind of shows you the process and the notation. Hope that's clear. So finally, this is what actually you need to get on and do. On eBrock, I've given you a file called Some Definite Integration Questions. This will be as a Word document or a PDF file. If you can just make sure you download that, please read it carefully, and there's some points to remember. Look at the example and make sure you can follow it, and then have a go at the questions. And it's important that you use the correct notation when you do those questions. When you've completed them, photograph your working and send me your answers so I can just check that you're doing it correctly. If you've obviously if you have any difficulties, have a go and do your best, and then you can always email me if you get stuck, and I can look at what you've done. Thank you.